Hello, everybody. This is Mr. Karlovsky, and I'm going to work with you today on the FRQ review packet, topic number 5, which we've called table questions. And let's go. So right out the gate here, we have our bullet points as usual about what you might expect on the table question type problems. We're going to look at a lot of these today when we go over number 1. For example, finding the rate of change from a table, also using a Riemann sum to approximate areas and other quantities. Um, Feel free to read through these. A big one I always think about is this first on the do's and don't list. I guess we call it a do. That remember that you do not know what happens between the values. That a table is nothing more than just little snapshots of moments along the function. So don't assume the values between unless you have a lot of extra information about whether things are increasing or decreasing and other details. Okay, so feel free to read the rest of these bullet points on your own. And we're going to do example number 1 together and then 2 and 3 on your own. All right, these problems that we have in the packet for sure need the calculator. And so let's look at number 1. Very typical water flowing in, water flowing out. So let's read. It says water is pumped into the tank at a rate modeled by W of t. So pumped into is for W of t. And we have a function, liters per hour for 0 to 8, where t is measured in hours. Water is removed from the tank at a rate of R of t liters per hour, and R of t is our table. It does say that R of t is differentiable and decreasing on 0 to 8, and selected values are shown in the table. At time t equals 0, there are 50,000 liters in the tank, right? As we know, you don't skip over any words. You read the entire problem, highlight, underline, all the important information. Now, part A is pretty straightforward. It says estimate R prime of 2. Now, it's not asking for R of 2, which we would also maybe estimate, but it's asking for R prime. Well, as we know, R prime of 2 is the slope at 2. Well, all I can do is say, well, I have the actual function value at 1. I have the actual function value at 3. And why don't we just find the slope from 1 to 3, and that would approximate R prime of 2. All right, so that's R prime of 2. And we would approximate this just by, like I said, using the values of 1 and 3. So R of 3 minus R of 1 all over 3 minus 1. Okay, and even if these numbers were so easy that you could do them in your head, do show the slope calculation for full credit. Okay, and so go to our calculator and we get negative 120. And now this is the slope, so it's not just liters per hour. It's liters per hour, so I'm going to write liters per hour squared. All right. Now let's move on to part B. It says use a left Riemann sum with 4 subintervals indicated by the table to estimate the total amount of water removed. Now it's only asking for the water removed, so that's why we need our table from the tank during the 8 hours. And then the second question, is this an overestimate or an underestimate? And give a reason for your answer. Okay, so let's look at our table. We're going to use the left Riemann sum. So for this, we're going to use 0, 1, 3, and 6, and their function values. And of course, the left Riemann sum is rectangles. We need to know the width of each rectangle. You can tell they are not all the same width. So I'm going to kind of scroll up and scroll down here. So for my left Riemann sum, I would have, I already forgot the first value. So for R of 0, we have 1340. And so we would have a width of 1 times 1340 plus, and then our second interval, we would have a width of 2 with 1190. And for our third interval, we would have a width of 3 using the 950. And for our fourth interval, we would use a width of 2 and the 740. And we go to our calculator and we get that this is 8,050 liters. Okay, so we now have the left Riemann sum to approximate the total amount of water removed from the tank. So now, is this an overestimate or an underestimate? And this is where every word matters. It tells us in the beginning that R is decreasing. And so if you want to think about it for a moment, if I know a function is definitely decreasing, then my left Riemann sum approximation will always be an overestimate, because no matter where I make my rectangle, if it's big or small, this is an overestimate. So let's just say what I just said, which is this is an overestimate because R of t is decreasing. All right, and that's all you need for that. All right, let's move on to part C, which is on another page. And all right, part C says use your answer from part B to find an estimate of the total amount of water in the tank, the total amount of water in the tank. So this is, sometimes we call this an accumulation function, or just the idea of we have a starting value and some stuff gets added, some stuff gets removed, and what's our finishing story. All right, so going back to the original, we have those three parts. We know that we start with 50,000 liters. And then we know we have a function. Finally, we're going to use the W of t function for adding water into the tank. And then we have our approximation from part B for the water removed from the tank. So let's just piece that together. So for the total amount at the end of 8 hours, we would have our 50,000 plus. And now we're going to do an integral, right? Because we have a function. We want the integral from 0 to 8 of our water in function W of t, dt. And then we're going to subtract the water out, which we just had in our answer from part B, which again was 8,050. And that's really all the work you need for this problem. You can go and define W of t in your calculator and just type this expression entirely into your calculator and see what you get. And we've gone to our calculator, typed it all in. Normally we round to 3 decimal places, but it does say to the nearest liter. So my number is 49786 liters. So this one is very much just a single calculation of a problem. Okay, and now let's move on to part D. Part D, let's read it. It says for 0 to 8, is there a time t when the rate at which the water is pumped into the tank is the same as the rate at which water is removed from the tank, and explain why or why not. Now, when I first look at this problem, I like to just go, oh, this means I want to know, does W of t ever equal R of t? Right? Because I say it's the same. However, how can we answer this question? Because we don't really know R of t. All we know is a table of just a few values. So instead of thinking of them as being equal, I'm going to talk about their difference, W of t minus R of t. Therefore, we want to know, when is their difference ever equal to 0? And the question is there a time where their difference equals 0? And that should hopefully look familiar to you, that we're going to want to use the intermediate value theorem. But we got to be very careful to show all the parts of the intermediate value theorem. Now, what can we find? Now, since our interval is from 0 to 8, we can check this at time 0. W of 0 minus R of 0. Well, those are numbers that we know. We can type in W of 0 and we can get R of 0 from the table. And all that really matters is that that is a positive number. So actually, I don't even care what that value is. I'm just going to state, and they just want to know the information. You don't have to prove it, that, hey, I found W of 0 minus R of 0, and it's positive. I also went to the end, W of 8 minus R of 8, other values I can get from the function and the table, and I found that difference, and it's negative. So I have that at 0, it's positive, at 8, it's negative. And then You just have to say the statement. We know that W of t is a continuous function, and since it told us R of t is differentiable, then we can just say that W of t minus R of t is continuous. If you remember, those are the three parts of the intermediate value theorem, that there's a positive, a negative, and we know the function is continuous. So we can say, therefore, the intermediate value theorem guarantees a value t in the interval 0 to 8 such that W of t minus R of t equals 0. And I think that's a good enough explanation to show that, yes, there is a moment where the rates are equal. Maybe you could even throw that extra sentence in there. This moment t is when the rate filling is equal to the rate removed. I'm not sure entirely whether that sentence is also needed, but definitely these three parts, here, here, and here for the IVT, would be necessary. All right, so good luck to you on doing problems number 2 and 3. Again, read those bullet points at the beginning of this section, and we're going to keep on keeping on, and good luck. Take care.